three-phase distribution systems that we were talking about last class. We have our Y configuration, and in Y, which was that, we have E line is equal to E phase times root 3, and I phase is equal to I line, or I line is equal to I phase. Delta which looked like that. We had our E line is equal to our E phase, and I line is equal to I phase times root 3. And these rules, if you remember what it's saying, and because I have both of them up here, you can see that the two rules are opposite for voltage and current when you go from Y to delta, and it's extremely important to get comfortable with this and get used to going back and forth between the two rules as we go to expand on the circuit and start having our power supplies and loads in the circuit. So we are going to do a three-phase power supply. So this could be either an alternator, or it could be 3 transformers coming off, and we're going to have a Y resistive load, and I'm going to say that we have 208 volts to keep it easy between, let's say that's line 2 and line 3. So obviously between line 1 and line 2 and line 3, and line 3 and line 1, we have 208 volts. And I'm going to say that I have a resistance per phase of 20 ohms. So that means that that phase sees 20 ohms, that phase sees 20 ohms, and that phase sees 20 ohms. I want to solve for everything in this circuit. I'm going to introduce power and then expand on that as we go through this. So let's break this down bit by bit and see if we can figure this out. So we have a line voltage of 208 volts. So E line is equal to 208 volts. And from the formula that we had seen before, we had E line is equal to E phase times root 3. So if we go to do this the other way around, we have E phase is equal to 208 volts divided by root 3. So if we do 208 volts divided by root 3, we get an answer of 120 volts. So that means that at our power supply, we have 120 volts. And when you're looking at three-phase distribution systems, if I have a supply that is in Y, that means that our load is also, if it's in Y, is also going to be 120 volts. So I'm at 120 volts here. I go out into the line, and I'm root 3 larger. And then once I get to my load, each of these individual branches is going to be root 3, or each of these phases is going to be root 3 smaller than the line. So I have 120 volts per phase. I go out to my terminals and then into the line. I come to the terminals of my load and down into each phase, and I end up seeing a value that's root 3 smaller, so I get 120 volts in my load. So 120 root 3 larger in the line, and then I go root 3 or smaller to go back into the load. So I have 120 volts per phase, so I can just write E phase is equal to 120 volts. And now we want to break down and figure out what the current is in the load. And we would just simply use Ohm's law again to figure out what the current is. And as you know, to find current, we would do our volts divided by our resistance. So our current is equal to 120 volts divided by 20, and I would see a current per phase of 6 amps. So I'd see 6 amps at in line 1, 6 amps in line 2, and 6 amps in line 3. If I expand from here, so I know that I have 6 amps in my load, and if I were to put an amp clamp on that, there's only one line or one phase that is seeing that current at this point. So if I continued with that amp clamp up into the line, obviously there's only one line conductor that amp clamp is on. So when I come back to my power supply or my 3-phase alternator or transformers, I have no change in current from my phase in my load all the way to the phase in my line. So I know from that I have 6 amps in each of my line conductors, which also means I also see 6 amps at my supply per phase. So I see 6 amps in line 2, 6 amps in line 1, and 6 amps in line 3. They are all the same. So I have 120 volts and 6 amps per phase, and I have 6 amps and 208 volts as my line values. And when I come back to my supply, I have 120 volts and 6 amps per line. So notice, because there's only one load, my supply values and my load values are the same, which makes sense because there's only one load. So whatever my load draws, my supply should also see those values. At this point, I want to look at power. If we look at single phase power, so if I look at this phase right here, I know that I have 120 volts and I have 6 amps, and those are the two pieces that make up power. P is equal to E times I. So if I was looking at single phase power, I would do 120 times 6 amps, and that would give me a value of 720 watts. because these are phase values, I'm going to be using watts. As we continue on, you're going to see that when I change from having a true power value, which is in watts, over to VARs, I'm going to find that my calculations do change a little bit when it comes to power factor, but we'll get into that later. But I have 720 watts per phase, so I have 720 watts there, I have 720 watts there, and I have 720 watts here. These are all real values. So if I had three separate plugs on three separate plugs on phase 1 and one in phase 2 and one in phase 3, I would see the cumulative amount, or the culmination of all three of these, of 720 plus 720 plus 720. So I would see a total power at my supply and at my load of 720 watts times 3. So I get a total power of should be 2160, or 2.16 kilowatts from that. And it makes sense, because each one I could physically see a voltage of 120 amps. I could put an amp clamp on it if it was a plug, or if it had an extension cord on it, and see that yes, I'm drawing 6 amps from each of those, combined of 720, 720, 720, which is 2.16 kilowatts. From this, I can derive a formula for 3-phase watts. Power is equal to my E phase times my I phase, and these are all phase values I'm using right now, because I was using phase values up here, so I'm going to put that into the formula down here. And to finish that off, we have 3 of them, so I multiply that by 3. So if I'm using phase values, as you'll see in a second, I do my voltage phase, my current phase, multiply that by 3, and that is my true power which is measured in watts. So I'm using phase values and multiply that by 3. Alright, moving on from here, we're going to create one more little formula for you. If I'm looking at power in my supply and power in my load have to be the same. There's, if I negate losses or whatever else in my circuit, I'm should have the same power seen at my supply as I do in my line conductors. Okay? I only have one load right now, so I don't have to add up multiple powers. I can just take that single power the way it is. So the way I calculated power in my supply is the exact same way as I'm going to calculate power in my load, which was 6 times 120, so 720 watts times 3. The question is how do I calculate my 3-phase power if I'm using line values? So these should all be the same. Power at my supply, power in the line, and power in the load should all be the same. However, we notice that we have a value of 208 volts. If I wanted to do 208 volts, times 6 times 3. That would give me a larger number than I would get if I was just using my phase voltage. So if I were to do that, I'm just going to pound this out quick here for you. I have 208 volts times 6 times 3 gives me a value of 3.744 kilowatts. If I were to use 208 volts, 6 amps, and a value of 3. So obviously there's a noticeable difference between 3.744 and 2.16. If you notice, when we went from our phase values to the line values, we increased this value by root 3 already, or the 1.732 that we were talking about. So this is root 3 larger to start with. If I take root 3 and multiply it by root 3, I get an answer of 3. So I'll show you why that's important here. If I have 120 volts here and I multiply this by root 3, it gives me this already. So I've already increased that phase value by root 3 already to get 208 volts. If I multiply my line value and my 6 by root 3 larger, I end up getting a value of 3. So if I plug that into the formula now, power is equal to, and if I'm using line values now, and I do E line times I line times root 3, this will give me the same answer as that. So this here, this is root 3 larger than this is. So if I multiply it by root 3 larger, it's going to give me the exact same formula as we have in the first case. So if you're only using phase values, I do E phase times I phase times 3. It gives me the total power of the supply or the load per phase. And then if I'm looking at line values, because this value is already root 3 larger, I can't multiply it by 3, but I can take my E line times my I line and multiply it by root 3. And now the two of these values are going to be exactly the same. It can be a little confusing to start out, but once you go through and you practice questions, it'll make your life or make things a lot easier as you go through. So I'm going to put an example on the board, and then you can pause the video and work your way through it. Before I end up doing it, so we have our first, and this is our supply. We'll do the same layout to start. And I want to solve for everything. And I'm going to lay this one out a little different than the last one. I'm going to put all the values at the bottom. So the values I want to find are, so in my supply, I have resistance, and I'm also going to have my power. In the line, I'm going to have E line, I line. Don't need to calculate resistance here because we're going to calculate it in the supply and then also in the load. But I can also calculate my power at this point, and then in my load I'm going to have a E phase, I phase, and the resistance, which will obviously be the same from this one to this one because I'm only having one load, and my total power. I'm going to use a value of 600 volts in my line, so we already know that this is 600 volts, and let's use 15 ohms per phase, so there, and there, all as 15 ohms. And let's go through and calculate this. So I've got 600 volts, and let's start on the right hand side this time, just because that's where our resistance is and our voltage is in the line. And if I take my value, 600 volts, I want to find the phase value. So we know that we take 600 volts and we want to divide that by root 3 or divide it by 1.732. So if I take 600 and I divide that by 1.732 or root 3, I get a value of around 347 volts, but we're going to use 346.42. Let's keep the decimal the way it is. 346.42 volts as our voltage in the phase. So if that phase voltage is 346.42 volts, that also means I have 346.42 volts on this side as well. So that we'll just write that beside the ohmic value, 346.42 volts. And if I want to find my current, I'm going to use Ohm's law. So I is equal to E divided by R. So if I take these two values here, 346.42. So 346.42 divided by 15 gives me a value of 23.09 amps. So 23.09 amps. And I can then find a three-phase power from this value. So per phase, if I wanted to calculate this out, I have a current of 23.09 amps times 346.42, and so I know per phase, so for one phase I know that I have a value of, let's do 7.999 kilowatts per phase, but I'm not looking for my phase power. I want to find what my three-phase power is. So that formula is power is equal to E phase times I phase times 3. So we already calculated that value out. We just multiply it by 3. But I'm simply going to take my 346.42 times 23.09 times 3. I know that's a little congested in there, but 346.42 times 23.09 times 3. And this gives us an answer of 23.996 or 7, depending on how many decimals you had left, kilowatts. So that is the total wattage for my load. So the total wattage for my load is 23.997 kilowatts. So that three-phase power is going to be not only seen there, it's going to be seen in my line conductors, and it's also going to be seen at my supply. So I know that I have 23.997 kilowatts. That was 23.997 kilowatts. And notice too, you don't have to use phase values to calculate that, but because all the information was here, that's what we used. We could have also used our line values, and I will show that in a second, just so you can see how that all works out. So I had 15 ohms, we can carry that information over. Ohms, and we had a phase current of 23.09 amps, which we know. The next question is, what is our line current? Well, we know that in Y configuration, whatever my phase value draws, my line value also draws the same amount. So I have 23.09 amps. So we filled out all the required information that we are needing to know. I'm just going to calculate three-phase power using line values, just so you can see it is the same. I'm just going to clean all this up a little bit. So formula we use, power is equal to E line times I line times root 3. So we have power is equal to 600 volts times 23.09 amps times our root 3, and if we plug that in to the calculator, we get 600 times 23.09 times 1.732, or root 3, and we get our 23.995. All depends on how much you rounded, but a couple decimal places one way or the other isn't going to make a huge difference at the end of the day, and that is kilowatts. So I do realize that that is a little confusing, but once you do it enough times, it makes life a lot easier. So I'd like to just throw one more on the board using delta, so you just get an idea of it, and we'll pound out all the math on it, and then I'll leave you with one more so you can do it on your own. And then I'm also going to put some homework questions online, not to take up for marks, but just for your own practice. Okay, so we have let's do delta power supply. And we're going to do a Y load. And I'm going to write things out the same way as I did with the other one. E phase, I phase, our resistance, and our three-phase power. We have our E line, I line, and don't really need to throw power in just because it is the same, so we'll just leave it like that for now. And we have our E phase, I phase, resistance, and our power again over on the end. Okay, we're just going to use some easy values to go through with. Let's use a line voltage of, let's do 100 volts for a line voltage. So 100 volts. And we are going to do a resistive load of, let's do 5 ohms per phase. Because our supply and our load are not the same type, so not the same type, meaning that one's delta and one's Y, our supply voltage and our load voltage will not be the same. They're going to change, and I'll show you why that is. So we've got our supply voltage of 100 volts, and the rule in delta is that our line voltage and our phase voltage are going to be the same. So if I went and took a meter and put a meter on this, I've got 100 volts. If I come down to my one phase, this is the same point electrically in, or per phase, that is in the line. There's really no difference between that. That's the same point electrically here as it is on these 2 points, and here as it is in these 2 points. So if I have 100 volts in my line, I'm going to have 100 volts per phase in my supply. So I have 100 volts seen here. When I get to the other side, I come across, but when I get to my load, I notice that I have 2 loads that split that 100 volts, but they are not in phase with each other. They're 120 degrees from each other, so I can't just divide them in half to separate them evenly. I have to divide the number by root 3. So I have to take my 100 volts and divide by root 3, or 1.732, and I end up getting a voltage of 57.737 as a voltage. So I have 100 volts in my at my supply, at 57.737 volts at my load. So 57.737 volts. When I go to do Ohm's law to figure out the current per phase, I have 57.737 volts. I divide that by 5, because I is equal to E divided by R. So 57.737 divided by 5 and that gives us a phase current of 11.547. So that is our current per phase. And if I were to take that current and I look per phase and I come out into the line, I'm not adding another load to it. It's still the same point electrically. So if I see 11.547 amps here, I should also see that in my line. All right. And if I want to look at three-phase power is going to be power is equal to our E phase times I phase times 3. So that would be power, I think you can see on the bottom of the board, yep. 57.737 times 11.547 times 3. So if I take those three values and I multiply them together times 3, I get a value of almost exactly 2,000 kilowatts. It's 2,000, so it's 2.0001, so 2,000 kilowatts for my overall power. So depending on your rounding, it might be exactly 2 kilowatts, or it might be just a little higher or lower. So that's the overall power. And because I only have one load, my total power of 2 kilowatts will not only be seen at my load, it's also going to be seen at my supply. The difference with this, so other than our voltages being different, so we have 57.737 and 100 volts, you should also be thinking as you go through this that if my voltage is less here, that would mean that there has to be a change in my current. So if my power at my supply is, or should be, the exact same as my power and my load, if voltage has went up, then there should be a change in my current, and we should see it going down. So if I have 11.547 amps seen in my line, 11.547, that means that at this node here at the terminal of my supply, I have 11.547 amps. But when I go to come to my supply, well, what makes up that 11.547 amps? I have this coil here from our power supply producing current, and I have this one here producing current, and it's the vector sum of these two that make up my 11.547 amps. Okay, so it's the sum of these, but they don't add evenly, so I can't just split that in half. But what I do know, because they're 120 degrees apart from each other, that this value is root 3, or 1.732 times larger than this current and that current. So I take my 11.547 and I divide that by root 3, or 1.732, and we have 11.547, and I divide that by 1.732, or root 3, and I get a current of, a bad current, as you'll see here, 6.66. Let's just add one more decimal just so it doesn't look as bad, 7 amps. So that is our ampacity of our supply. So we have 6.667 amps at the supply, we have 100 volts, and we have our still resistance of 5 ohms. And just so you know that that is the same, if we take these values down here and we have our three-phase power of 6.667, let's rearrange that. Let's do 100 volts times 6.667 amps times 3. So we're using our phase values here. So we take that times 100 times 3, and we get a power of 2.000. If we round up, we get to 1 kilowatts. So it doesn't matter if you calculate there or calculate there, you should get the same power. And this is a nice way, if you remember with parallel circuits and combination circuits, there were ways to check yourself. If you calculate your power here and then you do all the calculations and you get back to the line when there's only one load, your math should equal out. They should be the same. You should have the same power in the supply as you did in the load. So I'm going to give you one more example. I'm just going to throw on the board, and that way you can work on it between now and our next class. I'll just erase this quick. All right, for our supply, we are going to use a Y power supply, and we're going to have a delta load this time, and I'm going to look at a voltage of, let's do let's do, make it easy, let's do 208 volts for our line value. So that's our E line, and we are going to have a resistance of, let's do 4 ohms for our resistance per phase. So if you can work on that, go through and do that, and then find the questions I'm going to post on Fanshawe Online. You should be able to get a good crack at this. And then it's actually a really nice resource for this. Dalmars does a really nice job going through all this. So if you want more questions, or if you want things explained a little more thoroughly, you can end up going that route. All right, I think I'm going to end that there. So through the other questions that I had, if you stopped and worked that out, that should be enough for now to get you going, and you can spend a little bit of time on those practice questions. So I will see you guys in lab class and our next theory class. But other than that, that should be good. Hopefully things aren't too crazy up to this point. And as I said, over the next 2 to 3 weeks, we're just going to be expanding on this and building on this. So if you don't quite get things yet, no need to fret. We will be spending a fair bit more time on it. Okay, so have a good day, and I will see you guys later.